wait for people to come in.
So there's another meeting going on.
Oh.
Prasad,
Oh,
I am also there.
Okay, let's see. How do you start?
It's already started. I edit the motions and edit. Yeah, you get it. Then I have to walk in.
No, yes, thanks.
Try changing the slide.
Okay, let's start. Okay, so welcome everybody to today's keynote seminar. Today we are very happy to have Abhishek Mohapatra from Technical University Munich giving us this talk. Abhishek did his undergrad at Center for Basic Sciences, BAE. Then he was a PhD student at Ohio State. He was a postdoc at Duke, and then he is another postdoc at TU Munich. And today he'll be talking to us about various things on effective field theory and QC. Thanks. Yeah, let's start.
Thanks, Ranjan, for the invitation, and thank you for attending the talk. I know that this topic is quite new to everybody, so I will try to cover, give you the basic idea and be as simple as possible without going too much into detail. So that the whole game is developing this Born Oppenheimer EFT for studying these QCD exotic states. As you are aware, this Born Oppenheimer is the same Born Oppenheimer related with atomic physics or the movie seen. So the point is, as we know, matter is made of bound states, atoms, molecules, hadrons, nuclei in the QCD. And particularly among the matter, the non-relativistic bound states are lying at the core of, have been at the core of quantum physics. They have been associated with several revolutions like hydrogen atom quantum revolution, which led to a Nobel Prize, and November Revolution in 1974, associated with the discovery of the Chalmerian states. The non-relativistic bound states are interesting in the sense that they are multi-scale systems, and that's why they pose quite a serious challenge to have a QFT descriptions or a first principle QFT description, and being multi-scale, it's good ground to develop the effective theory constructions for such states.
Yeah. What is the multi-scale here?
You will see. I mean, the multi-scale is associated with the mass, the relative separation, binding energy, and everything. So just like in hydrogen atom, you have binding energy of m alpha square. Relative separation is given by 1 by m alpha inverse, mass of the electron. So this is the multi-scale system. So this talk is basically focused on non-relativistic QCD bound states of at least 2 heavy quarks. It's very similar to something like the hydrogen atom that we study in QED. So just starting with the basic QCD idea that we know there are 3 colors. In QCD there is this scale of nonperturbative physics, and there are 6 varieties of quarks. They are characterized into light quarks and heavy quarks, and there is this lambda QCD scale separating between the light quarks and the heavy quarks. We know that QCD spectrum only consists of color singlet states that we term as hadrons, and for a long time that we study in the usual textbook, these are usually mesons and baryons, which are bound state of 2 quarks or 3 quarks. So this was basically the conventional picture of hadrons until 2003. Like pions and protons, all known hadrons were classified as mesons or baryons. But things changed after 2003, where new species of states were discovered in the heavy quark sector, which are basically termed as the XYZ mesons. So they have more complicated structure, like written here: hybrids, tetraquark, molecule, pentaquark, hexaquark. And X3872 is the first exotic state that was discovered in 2003 by Bell. So from the QCD color perspective, I mean, you keep on adding more and more quark structure here to eventually get these color singlet states. So,
38 number.
which one?
3872.
3872 is the mass. X is the state, 3872 is the mass. Now they are changing the naming pattern, but in the literature, people still call it X372.
A872 is GB.
I mean, so I would first give you a simple picture of the two heavy quark system, which is a quarkonium
What is the
state.
new naming scheme?
Sorry?
What is the new naming scheme?
Chi-C1. So chi has to do with the fact that there are these chi, there are chi quarkonium state with quantum, which are denoted as chi, p wave quarkonium quantum number. So this is the quantum number of this X3872 is something similar to this Chi-C1p or Chi-C2p. So they are naming it as now naming in terms of these quarkonium business. So the simplest example is the two heavy quark system is this quarkonium, which is a color singlet bound state in the Cornell potential, which is attractive at short distance and having confinement behavior or linear behavior at long distance. And here is an example of the spectrum of the quarkonium states, both in the charmonium and bottomonium sector. You see there's a beautiful analogy like you have seen in hydrogen atom, where just like in hydrogen atom, you have these energy levels, and the analogous of energy levels are the states here. Now, exotics are more complex structure, as I have already indicated out. These are, as I mentioned, XYZ mesons are exotic states with two heavy quark. These are non-conventional states discovered after 2003, in a sense that they obviously do not fit the quarkonium spectrum. So one have developed well-defined methods to compute these quarkonium spectrum. But these exotic states are states that don't fit the traditional quarkonium spectrum. In some cases, have quantum numbers which are exotic, which do not appear in the quarkonium states. So, for example, these quantum numbers do not come up in the quarkonium states. In some cases, have charge. So, charge would tell you that at least there are 4 quark content. Like CC bar is 0 charge, but then in order to have charge, you need to add 2 more quarks. So that will tell you at least there is a 4 quark content existing. So example of such charge states are the ZC4430, ZB10650. Again, Z is the naming, 4430 is the mass in MeV. The way the XYZ is termed is Y are the states seen in E plus E minus collider, Z are the states seen with charges, and X are any other state. So state seen in some p meson decays or through some other decay channels. Interestingly, around 45 XYZ mesons have been discovered since 2003, but we do not know any way to understand theoretically how to understand the pattern of these states. So here I am showing you year-wise the XYZ states that has been seen in LHCb experiment, for example. You should note that there is, this is not the fully updated plot. That this has to be updated, but you should note that there is a state like X6900 which has 4 charm content. I think there is another state like X6600 with also 4 charm content that has been seen by Atlas.
So this is only experimental thing, but
This is experimental data.
You are saying that, but there is no theoretical.
There is no theoretical background. I'm coming to that. So there is no theoretical background on why these states are seen. If you ask me quarkonium, I can tell you how the quarkonium pattern or what next set of quarkonium states I can see. But
what kind of information they are supposed to provide, let's say, study these?
Mass, quantum number, decay channels, decay properties. These are 3 basic information. Then production, cross sections.
Those are experimental.
These are experimental data. Yeah.
I'm talking about what kind of physics information.
Like what?
QCD, if you understand QCD.
This is just QCD. This is QCD bound state. So if you have to construct a theory, you start with QCD. Try to get the spectrum. So first thing is you get the mass and the quantum number. Then you also need to get the decay rate calculation from QCD, production calculation from QCD. So all these needs to be matched with experiment.
QCD framework.
Yeah, it's the QCD framework that we are trying to develop.
So this X6600 and X6900. So at least one of them is the exact state of the.
No, these are 2 different states. For the time being, X6600 and X6900. So X6600 has been confirmed, has been seen in Atlas, but it has not been confirmed by other experiments. X6900 was seen by both LHCb and CMS. For the time being, these are not like these are 2 distinct states. They are not. We don't know whether they are excited to each other or not. And yeah, you
Why
should.
these are called XYZ?
So I told you that the naming convention is why are the states seen in E plus E minus collider? So they have quantum number 1 minus minus because E plus E minus will give you a photon, and the photon will eventually decay into some of these hadron states. Z are the states with charges, so the states that are seen with charge, like the ZC state I mentioned, and X is any other state that has been seen in some decay channels. So that's how the naming convention was set up.
Why the P's and this?
Sorry?
Why the P's and
The P are the pentaquarks states now. So these are also five quarks type states. I mean, they all fall under the purview of XYZ, but pentaquark is a. So XYZ were earlier used as a naming convention for mesons, pentaquark are baryons. At that time, when the naming convention was set up, there was no pentaquark states that was seen. But now we have also seen the pentaquark states. So these are 3 pentaquark, or 4 of them that has been seen.
and the name meson is because it contains
4 quark. I mean, 4 quark. I mean, baryon would have some baryon quantum number. Mesons have baryon quantum number to be 0. The most famous one that was discovered was this one in 2021 by LHCb, TCC 3875.
So looking at their masses, oh, you have an updated chart. Is this an updated chart?
No, this is not. I mean, this is like 2021 or 2022. So,
What was the next slide? Maybe.
oh, this was Bell. This is LHCb. This was Bell.
Okay, fine. I will wait for it.
Yeah. So this
Some
is
of them have been seen
both LHCb and Bell. So for example, these ZB states have been only seen at Bell, not at LHCb. But Bell has confirmed that these states are like existing. Obviously, some of the charm states have been seen by both. Then this is best 3 experiment in China, which only goes up to 6 GeV, so they obviously won't see the bottom states, but they have seen some of these states with what has been seen at Bell as well as LHCb. And interestingly, you should see something like ZCS, which is also state with a strange quark present. So as the detector gets upgraded, we are expected to see many more new hadrons in the near future, and therefore it is like a golden period for doing such hadron spectroscopy to understand this. So I want to just show you a more clear picture of how the pattern looks like compared to the normal quarkonium in the charm sector. So any state below the lowest DD bar threshold, so this is the DD meson threshold, are all conventional charmonium states. All these exotic states are lying above the lowest DD bar threshold, and they are marked here in the red color. And interestingly, you see several of these states are lying very close to the threshold. So there is a lot of these threshold effects that are important.
Is there any SU4 flavor symmetry
Uh,
which you can fit in?
No, not that of I know.
Some PDG has,
Sorry?
PDG has some weird stuff, right?
Yes. But,
Do these states fit in those kind of things?
I mean, these states are mentioned in PDG. So
No, what I was saying, SU4 flavor symmetry and start building these exotics. Do we cover all those exotics?
So for example, like here I'm talking about exotics in the heavy quark sector. There are exotics obviously also in the light quark sector. These are called A0, F0 mesons. We cannot address them in EFT, so like glucols and glucol states are exotics in light quark sector, like states of 3 quarks. We cannot study them in EFT, it's hard to study those states out. So this is specifically only exotic states in heavy quark. So theoretically, there has been multiple models for all these exotics.
The other question is, what do you call conventional? What do you call exotic?
Conventional is quarkonium.
Quarkonium.
Just quarkonium. Conventional is usual quarkonium meson. Exotic is anything beyond quarkonium. So multiple models of exotics has been developed. For example, molecule, compact quark, hybrids, pentaquark, doubly heavy tetraquark. And the problem has been every group has been either focused on one set of picture or the other, like some groups either study completely all of these exotic states in the molecular picture or in the compact tetraquark picture. And there has been only individual success in describing some of the XYZ hadrons, but no success in revealing any general pattern of these states.
So there, all of these are 4 quarks except the last hybrid.
Yeah, I mean, these are like, this is a compact tetraquark, this is a molecule, it's pentaquark, hybrid, and among tetraquark also there are multiple configurations. So I just shown some of them. Yeah, some of the configurations.
All these framework have some predictions also.
I mean, yeah, they make predictions like they start building. So they have all these model building connections. Start with the fact that we are starting with the quarks, but then they forget about QCD, and they have some random parameters. Construct a Hamiltonian with some random parameters to reproduce one state and make predictions for others. But if you start with the QCD Lagrangian and try to end up with those model Hamiltonians, it's just impossible and you can't do it.
And
So-
lattice can't do these things for now.
Sorry?
Lattice cannot do these things for now.
No, I mean, lattice does it. Lattice have studied like X3872. I will show you some result. It has also studied the TCC state. For lattice, gets difficult as the thresholds get more and more. As the states get closer to the threshold, so because they have to include more higher number of operators.
So can lattice predict 1372 from?
It cannot predict. I mean,
First principles?
it has indicated about X3872.
But the dream is that at some point, from first principles, it will predict 1372.
Yeah. The dream is that if we are able to do, if we have infinite like, power of the computer and everything, we can have 1,000 set of operators. Then lattice will be able to get these things. But lattice has limitations, and then they get very challenging for lattice as more and more thresholds are included in these studies. I'll show you the lattice results for X3872. So the question is there a coherent comprehensive framework that can put everything together in one picture? And this is where Born Oppenheimer EFT is kind of powerful. I just want to highlight one thing. For hybrids, the Born Oppenheimer is an isospin scalar exotic state, for which this Born Oppenheimer EFT and there are extensive lattice studies has been done for hybrid particularly because it's a easier extension to quarkonium. For others, there has been minimal lattice calculations, and the Born Oppenheimer EFT was developed recently, like by me and my collaborators, to address everything in one picture. So what is this Born Oppenheimer EFT is? So let us start with an exotic hadron with 2 heavy quarks. It can be QQ bar or QQ, and X is my any combination of light quarks. The hierarchy of energy scale in such systems starts with the mass of the heavy quark, relative separation between the 2 heavy quark, which is associated with MV, energy scale of the gluons or light quarks, which is lambda QCD, and binding energy of the heavy quark. So for exotics, one generally finds that this is the hierarchy of the energy scale, and this hierarchy of energy scale allows one thing to exploit is that the time scale for the dynamics of the 2 heavy quarks would be much larger than the time scale of the dynamics of the 2 light quarks. So you can consider the 2 heavy quarks to be static for the most of the time period for the light quark. So this is what the Born Oppenheimer approximation is.
Can you repeat the last sentence?
So the last sentence is, if I look at the motion of the light degrees of freedom, that happens at the time scale of 1 by lambda.
Yes.
That is a very short time scale compared to the time scale for the dynamics of the heavy quark. It happens over a very large time scale. So if you compare the time period, you can consider the heavy quarks to be static for the motion of the light quarks. This is exactly what Born Oppenheimer approximation is. That was.
Do we talk about like decay rate of these?
I mean, this is there has been studies for hybrid decay rates.
Yeah.
Tetraquark and pentaquark decay rates are in progress. So
when you start, I mean, would you call that as also dynamic?
yeah, I mean this is there.
Then if I compare it with like analogous light degree freedom, will the decay rate be longer for?
I mean it depends on what decay rate process you want to compute. For example, for hybrid decay to quarkonium, quarkonium has some set of hierarchy, hybrid has some set of hierarchy. Then there is energy gap associated. So based on where the energy gap sits, you can compute this processes. I mean, it's possible to do quadratic calculations. So the bound state dynamics basically in the EFT that we are focused at is at the scale mv square, and therefore one integrates out all energy scales above mv square. So you start with QCD, integrate out the heavy quark mass, end up getting NRQCD. Then you integrate out these two scales which are roughly of same order, and you end up getting Born Oppenheimer EFT or PNRQCDs. Both are used in the literature in the term. Why MV scale is of order lambda QCD? Just let me go one step back. Generally, I mean, our computations have found that hybrids have sizes of order of 0.7 Fermi. If you inverse that scale 1 by R, then you will find that it is roughly of the order of lambda QCD scale. So I don't want to go into detail of these, how this all process ends up. It's quite integrated, but if one wants, then either they can refer to my long paper or some review article.
You start with QCD.
Yeah, the first principle starts with QCD. Yes. You end up getting an RQCD. I mean, an RQCD is where all the lattice calculation happens. So that's.
So exotics, sorry, by definition is heavy quark, heavy anti-quark, and some light.
Yes. Heavy quark, heavy anti. So exotic is 2 heavy quark plus light. So it could be heavy. Light must be. I mean.
Otherwise, it's
I mean, there could be light. There could be all heavy like. Like X6900 is all heavy. There is no light.
Then you can't apply this.
I can apply. It's still applicable. I mean, when I say light quark, see, like quarkonium, these are 2 valence quark. I mean, it's a Q and Q bar.
Yes.
But there is a soup between the 2 heavy quarks going on. There is a lot of these gluon degrees of freedom that are existing in between.
Oh, the gluons are the free.
Yeah, yeah.
Light quarks.
Yes. So light degrees of freedom is light quarks or light. So in general, the EFT roadmap is you start with QCD, NRQ, then go to NRQCD.
So at some point you said 4C, right?
Yes.
C per C. So there, the light degree of freedom is a gluon, which is sort of
just like quarkonium, but now extended of. I mean, in a way, when I say quarkonium, yes, there are these CC bar states, but eventually they are in a soup of. There is a lot of these gluon excitations happening. And so 4 quark state is something similar, but a lot many structure now.
So only gluons, no light quarks.
I mean, there's no explicit valence light quark. But there's no explicit valence light quark. When I even say, so for example, if I have this type of system, there is explicit valence light quark, but eventually it is just a soup. Yes, I mean, light quarks can be annihilated, can be generated from vacuum easily. You cannot generate heavy quarks so easily from the vacuum. So in the quarkonium system, it is like a soup. Here there are explicit valence quark. In all heavy quark system, it's again like a soup of 2 heavy quarks with gluons. So depending upon the lambda QCD scale, either you study the weak coupling regime of this Born Oppenheimer EFT or strong coupling regime. The weak coupling regime is useful for states like J psi or epsilon 1s in the system that they are very low line states, and for them, for such quarkonium states, this hierarchy is well satisfied. Whereas for strong coupling regime, which is valid for exotics, since you integrate out lambda QCD, only color singlet fields exist, and matching coefficients are these non-perturbative potentials, as you will see. So let me give you a simple example of Born Oppenheimer philosophy, starting from QED system. So if you consider H2 plus molecule, which has 2 protons and 1 electron, the proton mass is 1 JeV, electron mass is about 0.5 MeV. There's a huge difference between the 2 masses. And the idea in atomic physics is that you consider first the protons to be static or moving very slowly, compute the electron energy. So first you fix the proton at a fixed separation R, then you compute the Schrodinger equation, electronic Schrodinger equation for fixed R, get these electronic eigenenergies, and then you introduce the motion of those 2 protons, and where these electronic eigenenergy will act as a potential in the nuclear Schrodinger equation. So the QCD states with 2 or more heavy quarks are analogous, where heavy quarks will play the role of nuclei, gluons or light quarks will play the role of electrons. Since it is QCD, lot of lattice inputs would be required for getting the static energies. I will not be able to solve the static energy in the QCD so easily by first lattice QCD. Yes, this is useful now. So there are certain BO quantum numbers that one needs to define. In the static limit, as I mentioned, the two heavy quarks are fixed. That breaks your spherical symmetry down to cylindrical symmetry. So first we consider, let's say, the two heavy quarks fixed along some axis. So you have cylindrical symmetry now. And because of this cylindrical symmetry, there are these conserved quantum numbers which are basically defined by this projection of angular momentum along the axis. The product of charge conjugation and parity is a conserved quantum number, and there is a conserved quantum number associated with reflection. Eventually, when you have the two heavy quarks very close to each other, then you regain back your spherical symmetry, and therefore you can label with the light degree of freedom quantum numbers with KPC. So there is a close relation between this KPC and lambda sigma eta. So here is the complicated Born Oppenheimer EFT Lagrangian, which is it should not. I mean, sorry if it looks scary, but okay. So let me systematically explain order by order what these things are. So the thing is, in the BOEFT Lagrangian, you label everything in terms of these LDF quantum numbers kappa, as well as in terms of the BO quantum numbers lambda. These are projection vectors that are introduced because, for example, if you go to this first definition, if k light is 1, your lambda could be both 0 or 1. Okay? I mean, the projection along the quark antiquark axis could be both 0 or 1. So these projection vectors are basically introduced to pick up either 0 or 1 in a sense. So these are projection vectors to pick up these BO quantum numbers in this thing. And here is the BO potential, which is the potential between the heavy quark and heavy anti-quark due to light degree of freedom. It has systematic expansion. So first order expansion is just the static potential, then order 1 by m cube corrections and higher order 1 by m cube square corrections. The 1 by m cube corrections are generally containing spin dependent potentials. There are some expressions for these 1 by m cube corrections in these papers. It's a horrible expression, but anybody wants, they can check these papers out. So if you get the equation of motion from this Schrodinger equation, let's for the time being forget about these projection vectors. If you get the equation of motion from the Schrodinger equation, it would be a simple Schrodinger type of equation that you are getting. Let me say that for quarkonium, for example, these projection vectors are 1, and if you solve the Schrodinger, if you get the equation of use, if you want the equation of motion, then it would be just a simple one-channel Schrodinger equation. For exotic states, it is more complicated because of these projections. So if I have to study beyond quarkonium, the idea in the Born Oppenheimer EFT Lagrangian is depending upon the light degree of freedom quantum number, you study either quarkonium, hybrid, tetraquark. Obviously, these states do not exist just individually; they will mix. So there are these mixing potentials that will end up mixing Lagrangian that will end up entering. But at first order, lattice QCD has shown us that, for example, this picture here, that these are, for example, the quarkonium states, these are hybrid states or tetraquark states. At first order, there is a gap of order lambda QCD. So, for example, if you want to study J psi, the lowest quarkonium and lowest hybrid state, they are not going to talk to each other, they are not going to mix. So, at first order, you can individually study them and then systematically include this mixing effect to accurately go to make more accurate predictions about your result. So an example of this mixing is like hybrid quarkonium mixing, tetraquark hybrid mixing, or tetraquark quarkonium mixing. So as an example, a simple example, epsilon 3s or epsilon 4s state. So these are CC bar, chalmonium or BB bar quarkonium state. They can mix with hybrids. Okay, because epsilon 3s, epsilon 4s would be sitting high in mass, which are very close to the hybrid states. But if you talk about epsilon 1s or j psi, they are very far away from the hybrid states, and therefore they are not going to mix. So hybrid quarkonia mixing is more relevant for us, for excited quarkonia. So here is an example of the, here is the general result for the wave function of the exotic state. Order by order. So first you fix the position R between the two heavy quarks, write the wave function of the light degree of freedom. Then you sum over all the positions of the heavy quark and sum over all the projections. This is basically what this wave function is. So yeah.
So here mixing is what? I mean, I can think of this as neutral mixing.
It's something. So yeah, it's very analogous to that. So for example, an epsilon 3s or 4s, the quantum number is 1 minus minus. I mean, just take it. This is known as okay. And the mass is roughly around 5 J. Okay. Yeah, 5 J. The lowest hybrid in the CC bar sector with quantum number 1 minus minus is somewhere around 4.95 J. So there's only a gap of 50 MeV. So this gap is very small. Whereas if you take epsilon 1s, this is something around 3 J. So here you see there's a.
It can exist in a superposition.
Yeah, exactly. Good. So basically my actual quantum state should be a superposition of these two states. So A times epsilon 3s plus B times hybrid. But in reality, since this mixing is already complicated business, in reality we first study individual configuration and then you try to improve upon this thing. So from that complicated Lagrangian, here is the radial Schrodinger equation that I get. Yeah.
So from the EFT, the only thing I can think of this is sort of like neutral mixing.
Yes.
So in your dreams, in this Born Oppenheimer EFT, can you predict the mixing angle, or will that be a free parameter?
Yeah, no. So free parameter in the sense that we know about how well the EFT constrains the mixing behavior in short distance as well as long distance behavior.
Mixing behavior means mixing.
Mixing potential. So everything here is in terms of this potential. So.
But there is also a mixing angle. If I think of the two-level system.
Yeah, you can translate.
That is like a fitting parameter.
It is eventually. So
ideally, it should come from something from QCD.
Yes. So it is it is in a way a fitting parameter. You can determine the order of magnitude of that fitting parameter by matching onto these PNR QCD calculation at short distance, or you can determine that fitting parameter by matching onto some experimental results. So in ideal way, it's a fitting parameter. Yes.
How much is the contribution of this?
So the mixing, the order of, so for example, in the case of hybrid quarkonia mixing, the effect can have up to like 30%. So yeah, 30%, 30 to 40% effects can come out. So for example, a pure hybrid state, after you include the mixing, would have 30% quarkonia component existing. So 30% is quite large, I would say. Yes.
What causes this mixing? What is the quantum number which is possible?
So the quantum, the total JPC quantum number is the same, and the mass has to be within the same order. So that is the requirement. If the quantum number is same but the masses are distinct, then also you can differentiate the state. If the state are close by, but the quantum.
Again, think of neutrinos. Masses need not be the same. Masses can be very different. Orders of magnitude different. Even
Yeah.
then they'll mix.
Sorry.
Even if the masses are orders of magnitude different, even then they'll mix.
Yeah, no, but here the
But
mixing
then the effect may be
suppressed. Here the point is the mixing of epsilon 1s and mixing with the hybrid is suppressed by this gap.
Yes.
So mixing is there, but it is highly suppressed. Whereas here the gap being 50 MeV,
Yes.
the mixing effect is larger.
The quantum mechanics will just say the quantum number is the same.
Yes. In general, the quantum mechanics says that the quantum number are same, they will mix. But because the large energy gap is there, that the large energy gap is what suppresses the mixing basically.
How do you extract the VC?
You match onto this PNR. I mean, you match. So, so basically, what you do is you perform some sort of a matching calculation between NRQCT and BOEFT to extract these mixing coefficients. They will enter as a Wilson coefficient in your matching calculation. Or another way to fix this mixing parameter is if you know some experimental result where these mixing are important, you try to experimental way. I mean, either you compute some decay rate and you try to match onto those decay rate values to extract these mixing parameters.
If you look at the mass distribution, suppose the resolution has resolution of this mass distribution of 5 MeV, let's say we can separate these two states.
5 MeV, I mean, so up to I think 100 MeV, the mixing would be much more important. Like I said, the farther the energy gap you have, the mixing is highly suppressed. So 100 MeV or 200 MeV, if the states are separated by 100 MeV or 200 MeV, the mixing gets important. 5 MeV, the mixing is much more important, I would say. So it would have serious implications on decay rates and everything, as well as spectrum. So, starting from that complicated Lagrangian, one gets this radial Schrodinger equation. The brief idea, the way one gets the Schrodinger equation is you have to use rigid body dynamics, considering the two heavy quark. So the system I'm looking at here is like a soup. I have Q and Q bar. If I join them by a line, this is like a linear rigid rotator, and you use the properties of quantum mechanics for linear rigid rotator to end up deriving these coupled Schrodinger equations. So let's not go into the detail, but the details are in that long paper, 115-page long paper. So anything you can want, you can find there. So the important thing is that in this Schrodinger equation, there is this middle term, which is the mixing term here. It comes from the fact that the static states have cylindrical symmetry because we started our exotic wave function as a superposition of multiple static states, but the operator, the del square operator has spherical symmetry. So basically, what will happen is that this mixing term will couple different static states with different BO quantum numbers. And I'll give you an example just now. So, for example, if I am looking at the lowest hybrids or tetraquarks Schrodinger equation, so for example, k equals to 1 is my quantum number. So k equals to 1 gives me lambda equals to 0 and 1. Lambda is denoted, 0 is denoted by sigma, lambda 1 is denoted by pi. And you see I have coupled Schrodinger equations between sigma and pi. Now the parity also enters into the picture, so if you have same parity states, they will mix, an opposite parity state will separate out. This is something called as lambda doubling effect in atomic physics. So the equations get much more complicated if you have as you increase the quantum numbers for the light degrees of freedom. K equals to 1 or k equals to 2. The quarkonium, so quarkonium, the k is 0. It's a one. That's why we get a one-channel Schrodinger equation. Now there are also doubly heavy baryons, which are more complex. I mean, like these are baryon states or pentaquarks, which are baryon states. Based on the LDF quantum number, one can end up getting coupled-channel Schrodinger equations or single-channel Schrodinger equations. So the main thing to note in the main takeaway is that okay, we have these coupled-channel Schrodinger equations now. The main takeaway thing to note is that on all these Schrodinger equations, we know everything here, but what we do not know are these static potentials. So how do we get those static potentials out? So in order to get static potential, let me again remind you, depending upon QQ bar x or QQx, the aim is to get the static potentials for all of these states or all of the states mentioned here. You should be wondering why I only consider the adjoint representation and not the singlet. The lattice results have shown us that, for example, states like proton J psi, so bound state, so proton and J psi, they would not form any bound states. So there are rigorous lattice calculations showing results that J psi and proton do not form a bound state.
What is the coordinate which is along the axis?
Which coordinate?
So it's a cylindrical symmetry.
The cylindrical symmetry only exists in static limit, when you do not include the kinetic motion of the heavy force. Gideon's theorem tells you that kinetic energy that the kinetic energy of the heavy quark would be roughly of the same order as the potential energy. So once you include that kinetic term, the del square term in the Schrodinger equation, you regain back your spherical symmetry, because you have to label your states with JPC quantum number. Yes, the angular momentum, parity, and charge conjugation. So first you study the static limit, where you have the two heavy quarks static. Then you introduce the kinetic motion using Miriel theorem. And as soon as you introduce the kinetic motion, you regain your spherical symmetry. So your total JPC is conserved. The point is that we need static potentials for all of these things. I already mentioned for hybrid there are multiple lattice QCD calculations. For rest others there are almost few or none to existent. And the aim is that if we know about these static potentials or BOEFT potentials, BOEFT can address all of these states. You just have to solve open channel equation. That's it. Nothing more has to be done beyond this. So the way lattice does these static potential calculation is they construct these NRQCD operators. So these are heavy fermion or heavy anti-fermion fields. These are the Wilson lines, and this is some light degree of freedom operator constructed to get the correct X quantum number. These are the projection vectors to get to these BO quantum numbers. Okay, so this in between insertion is done by the lattice to get to the correct static energy quantum number state. In simple terms, for example, in the quarkonium, they just solve this Wilson line with no insertion. So this is just one here for the quarkonium. Whereas in the case of exotics, this is like a Wilson line with a Wilson loop with insertion of these light quark fields associated with this piece here in blue line, corresponding to the BO quantum numbers lambda. And then in the large time limit, so basically they have these set of operators, they do certain sort of eigenvalue analysis, let these operators evolve for a long period of time, and at long time limit, eventually we get these eigenenergy states. So here are some set of operators that are suggested from Born Oppenheimer EFT for hybrid states. These are, hybrid is just QQ bar gluon, so we just have these gluon degrees of freedom. Then these are set of operators that has been suggested for the tetraquark candidates, and for pentaquark the operator is just horrible. So, I mean this is the operator for the lowest pentaquark candidate. Note that there is no lattice QCD calculations for these or these exist till now. For this there is only one, but for even pentaquark nobody has even tried.
In the last slide you say that for long enough time. So what do you mean by long enough time? Is there any reference time?
I mean, they start with some t equals to 0, then they go up to like like 10 lattice spacing or 50 lattice spacing units. So the time is defined also in the lattice spacing units. So they go up to some 50 or 20 lattice spacing. They plot these energy levels, and then they see where these energy levels get flattened out. So once they reach the flat surface, that is the energy level of the ground state. Because sorry. This is the quantum number of the light degree of freedom. So the quantum number of these light quarks or gluons. Yeah. So basically the point is just to give you a rough idea. A short distance analysis where you have two heavy quarks close apart. You have well-defined color singlet. For example, if you pick up the quarkonium, how do they happens? So if you have two heavy quarks close apart like quarkonium, you have a color singlet configuration in quarkonium. So at short distance, you have this color singlet field. You will match onto this Born Oppenheimer EFT field in this NRQCD calculation. In large distance, you have no such color configuration. The Q and Q bar are connected by a flux tube. This is like some gluon excitations or gluon energies happening in between. And you directly match this NRQCD operator used on the lattice two strongly coupled Born Oppenheimer unit. So what do all these gives us? So the interesting aspect is in the EFT business, if you do all these matching, for example, a simple case of quarkonium, let's say, the energy that we get is the singlet potential, is the usual, so maybe let me highlight the singlet potential, is the singlet potential minus 4/3 alpha S by R. Then some higher order corrections coming from multiple expansions. If you do it for the exotic case, because I am focusing only on the adjoint representation, so I have the octet potential, the QQ bar in color octet. Lambda, this parameter is like the effective light degree of masses.
What is short distance for you? What is the
So short distance. So short distance for me is something like. Let me just see. So R is 1 by MV. MV is greater than lambda QCD. So short distance would mean something like the J psi radius.
JCLD?
Yeah, 0.2 Fermi. Maximum up to 0.3 Fermi.
So you do it at 0.2 Fermi and then at 1 Fermi?
Yeah.
So two scales.
Two scales. Yeah. So yeah, if you want the order of magnitude of R, this is what you do it. So short distance is from 0 to 0.2 or 0.3 Fermi, and then from 0.3 to higher are long distance. So this expansion here that I have written is only from R ranging from 0 to 0.2. Yeah, so I was talking about what is this lambda parameter here. This is like, I mentioned that, for example, in the case of hybrid, this is the gluon. In the case of tetraquark, this is QQ bar. So this lambda is like is roughly the effective gluon mass or effective light quark mass in the bound state. Okay. So in the case of quarkonium, there is no valence quark, there is no anything. So there is no such parameter. But in the case of hybrid as well as tetraquark, you see there is a valence gluon, there is a valence quark. So lambda here is roughly the effective mass of this gluon and the light quark. Now, in the long distance limit, if you do pure SU3 case theory, there are results from effective string theory that tells you that how the energy should behave based on string excitations between the Q and Q bar. The string excitations basically are associated with this flux tube. But if you do the full QCD calculation, the unquenched calculation with light quarks, mixing with heavy light states gets important, and that mixing is determined from the BO quantum. So what is this lambda? As I mentioned, this is the effective gluon or the adjoint meson mass in the case of the QQ bar X states, or effective triplet meson or baryon or sextet meson mass in the case of QQX. So it is. So lambda is associated with the effective mass of X. So depending upon the color, if the color is 3, we call it triplet meson or triplet baryon if there are 3 quarks for X. If the color is 6, we call it sextet meson or sextet baryon depending upon the quark numbers. So in lattice QCD, the most recent lattice QCD computation of this gluelump, or is something called as the gluon, is done in 2024, and they get this effective gluon mass to be around 1.2 Jeff. The gluelump, the full gluon spectrum with 2+1 dynamical light quark was also performed in 2014, and this is what the result that they get in comparison to the lowest gluelump, which is 1 plus minus. And the adjoint meson spectrum, which is referring to introducing 2 light quarks instead of the gluon. It was back done in 1999. The calculation was quenched lattice QCD calculation with valence quark, so not the full QCD calculation. And they gave some results, predictions. As you see, there are very large error bars associated with those predictions. And after that, there is
form-wise, it is still linear potential.
With for hybrid, it is a linear potential. So let me go to the next slide. So hybrid, this is the hybrid potential here. So these are all linear potential because the long distance behavior is controlled by this effective string theory behavior, which tells you that as R increases, it will go by sigma R. But for tetraquark, pentaquark, it is not linear. This is the new result. So yeah, so for hybrid, as you see, these are potentials increasing linearly with R as like sigma R type, which is like Cornell. And interesting thing to note is that at short distance there are these BO quantum numbers that I kind of briefly mentioned you. At long distance, the string excitations are also associated with BO quantum number. And you see the BO quantum number is always conserved at all values of R. So a pi u BO quantum number at small r will always go to the pi u BO quantum number at large R. A sigma g plus prime at small r will always go to sigma g plus prime at large R. So these BO quantum numbers are all conserved at all values of R. This is an important observation. In the case of, this is the most recent calculation, so for the lowest, so for example, the quarkonium sigma g plus Cornell, and the lowest hybrid potentials, which are sigma u minus and pi u. Again, as you see, for all values of R, the BO quantum numbers are always conserved. And as you see, these potentials here, for example, in the case of hybrid, the sigma u minus and pi u are degenerated short distance. Here there is cylindrical symmetry, but here there is spherical symmetry. Okay, so as R tends to 0, there is spherical symmetry corresponding to gluon, but at finite values of R, we denote by sigma and pi because of the cylindrical symmetry. So what happens if you do, so the earlier result that I showed was quenched, which means there are no light quarks into your system. Now I'm showing you the unquenched, which is the system with light quarks. So let us look at the simpler case of quarkonium. So there is QQ bar state at some finite R. As you keep on separating R, at some point of time, you will break the string because you have these light quarks, dynamical light quarks into your system. Generating this light quark QQ bar pair would be would be energetically flavored, and once the string breaks, then you have meson-meson configuration. In lattice, they have seen, so this was the first lattice QCD calculation done in 2000, where they saw this string breaking behavior here, the red lines kind of bending towards the meson-meson threshold, and blue lines picking up from the meson-meson threshold for the linear part of the quarkonium potential. This can be understood in the Born Oppenheimer EFT language in the sense that the quarkonium potential is denoted by sigma g plus Born Oppenheimer quantum number. If you write the Born Oppenheimer quantum number for the meson anti-meson threshold, let's say the lowest DD bar threshold, which is S wave plus S wave, there is a sigma g plus Born Oppenheimer quantum number, and these two Born Oppenheimer quantum number is what mixes with each other. And this avoided crossing is referring to the fact that these two, at this intersection point, there is no crossing here. The quarkonium potential bends towards meson-meson, the meson-meson bends and picks up the linear part of the quarkonium potential. At the most recent lattice calculation done in 2024, I think yes. So they only focus here. This is a more recent lattice calculation of the same thing, except they included also the string breaking with strange mesons now. So DS bar here. This one is DS bar. This one is DD bar, and that's why 3-channel calculations. And as you see, they do not focus on the short distance behavior because the lattice QCD calculations are all affected by continuum pion states. So it is very hard for them on lattice QCD side to solve them. The string breaking radius for DD bar is around 1.2 Fermi. The string breaking radius at DS bar is around 1.3 Fermi. If I add further another channel, the string breaking would keep on going. So pictorially, if I did not have light quarks, everything would go linear. So no light quarks. Now if I introduce light quark, my quarkonium will bend. Something will pick up. If I have another threshold, this will bend, something else will pick up. If I have another threshold, this will bend and something else will pick up. So the string breaking behavior would keep on going and going the more thresholds you keep on adding. And this string breaking behavior is what causes the mixing between quarkonium and these meson states. For the time being, I would skip this. This is important for the hybrids. So let us skip this. So the important observations that one needs to make from this results that I have shown for the lattice is that BO quantum number is particularly conserved at all values of R. Different BO quantum numbers intersect with each other. So let me just go back to the hybrid slide here. So you see different BO quantum numbers like sigma u minus intersecting with sigma g plus prime and so on. But the same BO quantum numbers cannot intersect. So as I showed you in the string breaking case, the avoided crossing happens between the BO quantum numbers which are the same. So if you use this principle, then for tetraquark case, what one finds is that in the case of tetraquark, so I'm talking about QQ bar and QQ bar. If I have my Q and Q bar far apart, then I can already generate a meson configuration, individual meson configuration at large values of R. And so quark configurations can be rearranged to have the two hadron state, and the BO quantum number conservation forces that the potentials would look something like similar to molecular physics, where molecules are going into constituent atoms when the internuclear separation is large. So, for example, here is the full potential for the tetraquark. So it starts with some adjoint representation at short distance, and then it eventually matches onto the DD bar threshold with BO quantum number sigma u minus. This is another tetraquark configuration starting with 1 minus minus adjoint configuration and matching onto the DD bar threshold with BO quantum number pi g and sigma g plus. So why these appears? So here is a simple example. So you have QQ bar in color octet. If the two light spin could be 0 or 1 based on the spin, you have these BO quantum numbers. If you do the same thing for meson anti-meson, just look at the light quark quantum numbers, you again get 0 and 1 and corresponding similar same BO quantum numbers. So sigma u minus here would go to sigma u minus, sigma g plus would go to sigma g plus, pi g will go to pi g. So the behavior is very similar to something like the Lennard-Jones potential in atomic physics. So meson anti-meson threshold at short distance is connected with adjoint meson, and they will. This is the whole tetraquark game is. So this behavior is not yet confirmed by the lattice QCD. I mentioned to you that.
Can you go to that block?
Which one? This one? Yeah.
Yeah, so this happens that when it's negative, then it's bounded, and then if R goes to infinity, then two separate states are formed. That's why it's going to a zero.
Threshold.
And when R is very close to zero, then it
Shoots up. Just like in Lennard-Jones, like if you have two molecules, there is this repulsive potential appearing from electromagnetic forces. So the potential shoots up. Here it shoots up because of the adjoint representation. So we have the two light quarks in adjoint representation octet. The octet is repulsive. Okay. The octet color potential is repulsive. The singlet color potential is attractive, but octet is repulsive. So you see the picture is very similar to like a Lennard-Jones potential. The point is that this behavior is predicted by the Born Oppenheimer BOEFT, but it has not been confirmed by lattice. Lattice needs to confirm this. As you already see, lattice did not go to small values of R because of lot of noise with the pion configurations out. So they are not able to separate the pion signals from the energy configurations shown. And depending upon isospin 1, whether you are working in isospin 1 configuration or isospin 0, so here is the full isospin 0 thing that should be seen on the lattice. This you can think of as DD bar, this is D bar, D1 threshold. So I just showed you the lattice plot, a few things about. I mean, basically you should compare, you should compare this part, for example, with the part that is shown here. So the Born Oppenheimer BOEFT basically tells you the complete behavior starting from short distance to long distance limit. And therefore, the key takeaways are tetraquark static energy behavior is adjoint meson behavior at small r, heavy meson pair threshold like dt bar at large r, avoided crossing with quarkonium static energy in the case of isospin 0. If I add hybrids, there would be further avoided crossings, but that complicates the matter. You get the picture in the simple case.
So where does that minimum occurs? So minimum of the potential.
The minimum? I mean, I told you that there are tetraquark states that we have seen at 3800 MeV. In order to see those states, I need that minimum. Otherwise, there is no way you have a tetraquark state. So I will next. I'm going to the tetraquark now. So this minima is required. So first question you should ask is how much is the DD bar threshold? The DD bar threshold is somewhere around 3.9 J. Okay. So this horizontal line is at 3.9 J. I have seen experimentally we have seen states below 3.9 J. So in order to understand those states, you need the minima below 3.9 J so that you can explain those states out. Okay? So this minima is that's why required. Okay, so this is more particularly important for lattice community in the sense that, like I said, for a long time the lattice is poised with these pion configurations at short distance, and the operator that we suggest in Born Oppenheimer EFT gets rid of this problem. It does have zero overlap with quarkonium plus pion configurations and have some finite overlap with the meson. So this is very important for determining these eigenenergy states or the potentials on the lattice. The takeaway is that adjoint meson operators are good operators for lattice computation of these tetraquark potentials. They should be considered in the lattice QCD calculations, and this is something an effort that we are trying to push now. So let me show you the application of all these to X3872 and TCC. That's quite quick. I will do. I just want to tell you the X3872 is the first exotic state, as I mentioned. Quark content is CC bar plus light quarks. Quantum number is 1++, isospin 0. The mass is extremely close to the D star 0 D0 threshold. It's within 100 keV. So if you like, here it's like 70 keV. Order of magnitude is 70 keV here. And you see this extremely narrow threshold, extremely narrow resonance. The width, the decay rate is about like 1 MeV only. So how do you do it all in this tetraquark analysis of the Born Oppenheimer EFT? So if I do the isospin, so this is the complete multiplet that I am showing that I get from the Born Oppenheimer EFT for the tetraquark states, considering the lowest light quark spins. So the 1++ is sitting here, isospin 0 channel. In the isospin 0 channel, this would be X3872. In the isospin 1 channel, the 1 plus minus, these are well-known states associated with ZC and ZB. There need to be mixing between these two states to explain the whole complete spectrum of these four states. And this is associated with something called as predicted light quark spin symmetry by evolution and Eric. So for X3872, you basically use this potential, the isospin 0 potential that I mentioned, take the avoided crossing with quarkonium, so you solve this multi-channel, like 3-channel Schrodinger equation here. For the time being, I'm doing spin average analysis because spin corrections, including spin corrections, the full spin corrections, will increase this 3-channel to something like 6 or 7 coupled channel Schrodinger equation. So let us first do the 3-channel and systematically go ahead. So if you do the 3-channel Schrodinger equation solving, this G of R are the mixing potentials between the G of R is denoting this avoided crossing mixing potential. This is the mixing potential behavior that is motivated from the EFT side. If you do all of this, then the result that you get is something like 8 to 13% of quarkonium component in X3872. The tetraquark percentage is about 92% broken into sigma and phi components. The radius of this state comes out to be about 15 Fermi, and in the bottom sector we get a deeper bound state about 15 MeV below BB bar threshold. The critical adjoint meson mass that is required to get this state is 920 MeV, so this is a prediction that needs to be confirmed again on the lattice. So to account for the spin splitting, what we did is there are some known results for spin splittings from hybrids. The tetraquark computation of spin splitting is still pending. It's a complicated job. So for the time being, let's take the results from the lattice QCD spin splitting results for hybrid and use them here. You can question them, but yeah, I mean, this is just a first set of calculations showing the results. So what happens is if you include the spin splitting, there are these 4 states. The X is my 1 plus quantum number, and it comes right at the DD bar threshold where it should be. The other spin partners of the X are distributed like as follows. And the main point is that the 1 plus state is identified with X, the 1 plus minus state is identified, is having this mass, which could be identified with with an exotic state known as X3940. The 2 plus state is a prediction of ours, so with a mass around 4 JeV. The 0 plus state has a mass around 3.95 JeV. This is also indicated this has also been indicated in the lattice calculations back in 2021. Only this multiplet, so I showed you several multiplets here in the tetraquark. Only this multiplet is going to exist. All these other multiplets will not be having any more states. There will be no bound states associated with any other multiplet, with the critical adjoint that is mentioned here. So the importance of this quarkonium, why this quarkonium percentage is important. There has been studies of radiative decays of X3872, for example, decay to gamma psi 2s and gamma j psi ratio. I mean, this is there has been studies of this ratio, which is X3872 decay to gamma psi 2s and gamma j psi. LHCb has estimated the value to be 1.67 with an error bar of 0.25. Our estimate is 2.99 with large error bar because in order to make this estimate, one has to take some NRQCD calculations. So we just borrowed some NRQCD calculations for some model calculations from somebody else. So rigorous calculation needs to be done, but okay, roughly the order of magnitude matches. Now there is lattice QCD also has indicated that this quarkonium component needs to be present in order to get the X3872 signal in lattice. So if the lattice QCD calculation is just performed with DD star operator, they do not get any X3872 signal. They only get the X3872 signal when they include the CC bar along with DD star. So this is an important point to note. So if they do it without CC bar, they do not get X3872. If they only get signal with CC bar included. And there is this compositeness business. There has been study. Compositeness has to do with the fact that what is the quarkonium percentage or the compact component percentage in all these examples. So our 8 to 13% it basically comes up naturally. I mean, we did not have to do any model building or anything. We just took the lattice result, fitted the potentials, used our predictions of Born Oppenheimer BOEFT, and 8 to 13% comes up naturally for quarkonium component in X38. This 8 to 13% quarkonium component is also crucial for doing these production calculations of X. All the production calculations have indicated that X needs to have something like 5 to 10% quarkonium component. And so our results are well within that estimate that is required. The another thing is this TCC, which is the longest lived exotic particle with a decay width of around 50 keV. So you can again, I mean, here the multiplet is slightly similar because poly-exclusion principle comes into picture. There are no bound states in the bad diquark because the mass is heavy. Only the good diquark will have bound states, and the TCC is associated with this good diquark, bound state in the good diquark here, 1 plus. Here you just solve one channel Schrodinger equation, and this is what the result we get. We get a state with radius about 8 Fermi or larger. We get deeper bound states in TB in the bottom sector, and slightly less deeper bound state in the PC sector. And I'm showing some predictions from lattice QCD process. So here is what our TBB and TBC predictions. So this is our prediction here. compared to all the lattice QCD studies that has been done for TBB and TBC. So you see, I mean, it's quite well in agreement with what we get. So yeah, so it's quite interesting. So I would like to end up or summarize the work is that the Born Oppenheimer EFT is a tool starting from QCD principle and basically exploits this Born Oppenheimer approximation from atomic physics. It's a model independent and systematic framework, so you can systematically improve upon these potentials order by order, and there's a lot of lattice QCD inputs that are required here. I mentioned what should be the behavior of the tetraquark and similarly pentaquark static energies. If I'm talking about QQ bar system, they should have adjoint meson or baryon behavior at small r. They should approach heavy meson pair or heavy meson baryon threshold at large r. For QQ system, it's a triplet or sextet meson at small r. And in the case of QQ bar, avoided crossing with quarkonium gets very important for the tetraquark case. Like X3872, you see, the avoided crossing is what gave us this mixing with quarkonium. A lot of lattice inputs are needed, really. I mean, we made some predictions on the critical adjoint meson mass based on X and TCC, but these needs to be confirmed on the lattice. And the aim is to understand the complete pattern of all the 45 states and just showing the results for 2 states here. But all the 45 states as well as pentaquark needs to be done. I just want to motivate you that there is new pentaquark state with isospin 3/2 in lambda C plus pi minus D minus channel. So there is this resonance peak that they observe. Isospin 3/2 because pi minus is -1 and D minus is -1/2. So total Z component isospin is 3/2, which indicates that the isospin has to be 3/2 here. The lowest isospin has to be 3/2. All the pentaquark states that has been seen till now are only 1/2 isospin. So, sorry?
Let's see, we preliminary.
Yeah, it's a preliminary result. I mean, it was shown in one of the conference, but it is not yet out, I think. But they want to do perform the analysis completely. So the LSCB is doing this. So I want to end up with the thing. Hopefully, I gave you the brief idea that XYZ meson is really an elephant that we are trying to address. All these models are addressing some parts of the elephant, but not the whole picture of the elephant, which needs to be addressed together. So the aim is that BOEFT addresses everything, the whole complete elephant in the room. Thank you.
Thank you, Abhishek, for the nice and interesting talk. Are there more questions? What do you have in the talk?
So we were expecting that this approximation will work for all like states.
Yeah, the approximation is just separating the time scale. And the approximation is just telling you that at first order I will do static business. Then obviously, like I mentioned, the mixing gets important, the spin dependent corrections get important. But the point is, as you see, it is a very systematic approach. I mean, 0th order in mass expansion, you have the static limit, which is what this approximation is. Then you go 1 order in mass, NLO, you include spin or mixing effects. You can also include threshold effects systematically. So yes, I mean this is at least the full picture. I mean, it is giving you theoretically the full picture completely. The only problem in this whole business is we do not know a lot of information about the static potentials or the spin dependent potentials from that system. So that is where this constraint comes to us. I mean, there, since we do not know, we have to do some phenomenological modeling there, obviously. But yes, if I would have known everything from lattice, if lattice was able to provide me everything, then one can do these calculations.
So you have shown one graph where I mean we have in one case we have the cylindrical symmetry and another case I think one the radius is small, then the spherical symmetry.
Yeah.
So you had like you had a graph. So I think that's sort of an assumption. I mean from the calculation when we start the calculation that is the assumption, right? I mean
No, there's not. It's not an assumption.
I mean the particular value R should be less than some point.
I mean the thing is, for example, if you take epsilon 1s or j psi, such quarkonium, these are the lowest quarkonium states. Epsilon 1 is the lowest bottomonium state. Epsilon j psi is the lowest harmonium state. These states for a long time has been known that the radius is 0.2 Kelvin. And these states, you can get these bound states just in the Coulomb potential itself. You do not really need the linear potential to study JSI. I mean, the effect of linear potential on JSI is negligible. The Coulomb potential is only valid for short distance. And this validity only happens until the radius of the JSI, I would say. So that is how we know that where the short distance limit lies. I mean, it's not a guess. So for example, the string breaking that I showed you, it happens at 1.2 Kelvin. This is a very large effect.
So in this result also, the degeneration starts quite well at 0.2.
Sorry?
I mean, in this is the result. So here, does the degeneration start?
No. The degeneracy does not start at 0.2. I mean, the degeneracy starts here at r equals to 0. I mean, this is a lattice QCD computation. You see, they have really taken a lot of effort to go at small distance. I mean, it's a lot of computation that one needs to do, and you already see the data points merged together. The EFT is what tells you that there is degeneracy, and it's somewhat an indication that they see this repulsive behavior. Obviously, they will not be able to see the full thing, but okay, they have indicated that the energy is kind of approaching together. So the degeneracy is happening.
In other, I mean, the CFT way, it starts at 0.1.
Sorry?
In the EFT way, yeah, the EFT calculation, so does it exactly shown that it starts at 0.2? I mean,
Like, what do you mean by it starts at 0.2?
I mean, these two graphs or these two plots.
Yeah,
It's matching at 0.2.
I'm matching at 0.2. Yeah, I'm matching at 0.2. EFT I'm matching. So when you fit these potentials, you have this smaller expansion, you have this longer expansion, you are matching at 0.2, these two expansions together. So when you fit this.
So how much when you're writing these operators which you can calculate them on lattice?
Yeah,
So how much is the, and I mean, you're essentially tuning the entire thing.
yeah, essentially
You're tuning the entire thing so that you can match with the lattice.
yes. So the thing is, like,
Are we missing something there, or
no,
this
so,
modeling, is it sufficient?
no. So okay. So we are writing in terms of Wilson loops so that we can match onto lattice. The operators are coming up all naturally. I mean, the operators, there is no tuning happening there. It's just that in the lattice QCD calculation, they need to know what set of operators they need to consider for a state. If they do not know, they just construct, like for X, like I said, they first included only the DD bar operators, a bunch of these DD bar operators, and they say that, okay, I cannot see X3872. Next, they included CC bar operators, and they see some signal. But the better your operator overlap is on the state, the better chances you have in the lattice to get to the good signal. So the operators that we are suggesting, theoretically we prove that it has zero overlap on these pion configurations. So for most of the time the lattice QCD is poised with the fact that there are these continuous pion states and they are unable to differentiate. So since the operators that we suggest, we theoretically prove that they have zero overlap on the pions. So we kind of hope that if the lattice takes these operators and do the computation, they should be able to get the good signal out. Now, how much costly it is or how much difficult it is, this is something which should be discussed by a lattice expert. This is not where.
Okay, that's the technical issue with the lattice.
Yeah.
But I read that it shows this thing, but in real life we have pions also, right?
Yeah, in real life, so my point is that, like, okay, lattice consider pion operators also. My point is that they should also add this operator to their list to do the full analysis. They should not be doing that. Okay, we suggested this one operator. They should take the one operator and do the complete analysis. You will never get good results with this just one operator. On the lattice, they have some 6 operators. We are suggesting that also include these whatever operators that come in from EFT included in your analysis. Then we are hoping that with these operators accounted for, that particularly probe some part of the physics, you should be able to put good signals out. So they do need to consider the pion operators. There is no absolutely doubt. They do need that.
There are no other questions. Let's thank Abhishek again for the nice talk.